This video is on Hess's Law. So this is a different way of finding an enthalpy for a reaction. So it has to do with a couple different things. So total enthalpy change on converting a given set of reactants to a particular set of products is constant. So it's independent of the way it was carried out. What that means is no matter which way you get from your reactants to your products, it's going to be the same total heat change. It's also independent of the number of steps. So it doesn't matter how many steps you take to get to your final products. If you can do it in fewer steps versus more steps, it's still going to be the same total heat. So if a reaction can be carried out in steps, then the total enthalpy change, what we're trying to find, is the sum of all the individual enthalpies. So we can add up all the steps to get what we're actually trying to find. This is helpful because we can find that enthalpy changes for reactions that are hard to measure in one step. Sometimes it's hard to actually perform that reaction or find the energy for that particular reaction. So if we can do the steps to get there, we can just add those up. So this is kind of like a little bit of problem solving, a little bit of like puzzles, like how can we manipulate these reactions to get the one we want? So there's a couple ways that we can manipulate. So I'm going to write over on the side that we can manipulate reactions by, there's kind of two main things. So one is we can reverse them. So when we reverse a reaction, our reactants turn into products, right? Typically, we can just turn them around. So products become the reactants, reactants become the products. When we do that, and this was talked about in a previous video, delta H changes sign. So if it was positive, it becomes negative. If it was negative, it becomes positive. Another thing we can do is we can multiply reactions, and this can be like by a factor of 2, 3, 4. It could also be a half because multiplying and dividing are actually the same mathematical operation. So it could be multiplying by a half or dividing by 2 or 3 or anything like that. When you multiply, your delta H multiplies too. All right, so let's do this one right here. We'll do two examples. So it says consider the two reactions involving iron and oxygen. So I'm going to label this reaction number 1, reaction number 2. And these we know the enthalpy changes for. Here's the one we're trying to find though. And we want to find in kilojoules just like we're given in the previous one. So what we have to do is we have to figure out how can we manipulate 1 and 2 so that when we add them together, they will equal this final one that we want. So I'm going to look at this as like, where do I have reactants and products? Are they in the right spot? Which would tell me I need to reverse them if they're not. And then do I have the right quantities, which would tell me if I need to multiply or not. So looking at my overall reaction, I've got this FeO, iron 2 oxide over here as a reactant. And up here in number 1, I have it as a product. So it looks like I'm going to have to reverse this one. And then if I also look at this, there's a 4 here, and I've got a 2. So I think I'm also going to have to multiply it by 2. So I'm going to rewrite that whole reaction with these things done to it. So I'm going to do, oops, hold on. There we go. I'm going to do 4 FeO, right? Multiplied it by 2, flipped it over as my reactant, and that makes 4 Fe and 2O2. So I flipped reactants, products, I multiplied everything by 2. Now let's look at some other things. So let's see, oxygen is in both reactions. I'm not going to mess with that. I'm going to hope that just works itself out, but I'm going to look at this one right here. And it says Fe2O3 and 2 of them. That's exactly what I have here. So I'm just going to leave this one as is. So I'm just going to rewrite it down here by this one. So 4Fe plus 3O2 makes 2Fe2O3. And if you've noticed, I've lined up my yield signs because now I'm going to look at this and I'm going to add these together. All right. I'm also going to write on what the delta H's are as I change these. So this first one, I reversed it so it becomes a positive 544 and I multiplied it by 2. So I do that for this as well. My second one, I kept it as is. Okay, so now I want to add these up my two delta H's, but I have to make sure my two reactions added up equal the one I'm solving for. Oops. So if I have something on the reactant and the product side, both sides, it will cancel out. It's like subtracting it. If I have something that's the same on the reactant side of two reactions, I'm going to add them together. So what I notice here is that I have 4 irons on the reactant side here and 4 irons on the product side in my first reaction. So these divide out. Okay, so they aren't part of my final reaction. And then what I also notice is that I have O2 in both of them. And I have 2 here and 3 here, which means one of these cancels out, and I'm left with just 1 O2 here. Think of it as like saying like reactants minus products. So if I have 3 O2 minus 2 O2, I'm left with 1 O2. So now nothing else cancels, so now I'm going to rewrite this. So I've got 4 FeO plus O2, which makes 2 Fe2O3. And I can check this by saying, is it still a balanced reaction? And let's see, I've got 4 irons. I've got 4 plus 2 is 6 oxygens. 2 times 3 is 6 oxygens. So this is a balanced reaction. Is it the one I was trying to find up here? Yes, it is. Which tells me now I can add my delta H's. So when I type these in my calculator, add them up, I get negative 560, and these are in kilojoules, and that is the enthalpy of this reaction. So let's do another one. And if you'd like to pause and try this one on your own, and then watch me do it, by all means, go for it. All right, so this one, all right, I'm going to do the same. I'm going to label 1 and 2. Okay, here's what I'm trying to find. And let's look at what we have here. So I've got H2 I need here on the reactant side. I've got that right here, but I've got 2 of them. All right, and I want the, okay, so I'm going to say, well, I'm going to have to take this and maybe multiply by half, divided by 2. You could also write that same thing. Okay, and then I'm going to ignore the oxygen because it's in 2 spots, and that's just going to get messy. So let's look at this, H2O2. All right, well, I've got that on the reactant side up here. So I'm going to need to reverse this one. And I'm also going to look at the quantity. I only need 1, but I have 2. So I'm going to also need to multiply by half or divide by 2. So now I'm going to rewrite these. So number 1 rewritten, reversed and divided by 2 would be H2O plus 1/2 O2 makes H2O2. Be careful, make sure you're copying things correctly. And my delta H will be reversed, so positive 200 times 1/2. All right, number 2, I'm just multiplying it by 1/2. So I'm going to get H2 plus O2 makes H2O. So my delta H is just negative 600 times 1/2. Oops. All right, so we can add these together now and make sure we get our reaction we wanted, and then we can add our delta H's. So I've got H2O on a reactant and product side. So subtracting those, they divide out. I'm going to do that in red. All right, and then let's see. Oops, I forgot to do this. I made a mistake. I hope you caught it. My O2 right here should have been 1/2. All right. So I can add these together, right? Because they're on the same side. So they will add up to 1 O2. So now I can rewrite this as H2 plus O2 makes H2O2, which is exactly what I wanted. And then I can add up my delta H's. If it ever happens, let's say, where you made that mistake where you forgot that 1/2 of O2, and you write your reaction when you add them up, you'd have gotten 1.5 O2s. And if you realize, like, if you looked up at this and said, well, that doesn't match this one, you know you did something wrong. So that's where you have to go back and redo all your steps, or check all of your steps to try to find your mistake. Like that should be assigned to you. All right, so when I add these up, it ends up being, let's see, 100 plus negative 300. So it's going to be negative 200 kilojoules for the enthalpy of this reaction.